Welcome everyone to She Has the Floor for December 21st, 2021. Today's talk is The Time for Girls and Women in STEM is Now, and our speaker is Dr. Judith Olson, Senior Physicist and Head of the Atomic Clock Division at ColdQuanta in Boulder, Colorado. Thank you everyone for being here. We began this series shortly after the equinox at the beginning of fall. We are at the solstice, winter solstice in the Northern Hemisphere, and we're just delighted to see everybody. So thank you. Here is our roadmap for today. We'll begin with some brief introductions, and then we will move into our STEM chat for today with Dr. Judith Olson. From there, we'll go into Q&A. You'll be welcome to ask questions during any point in Dr. Judith Olson's talk, and then we'll officially have Q&A after she concludes her STEM chat. And then finally, as we have been doing for the last many weeks, we'll ask for your favorite takeaways from today's event. We'll put those into a word cloud and email them back to you in the next day. I'd like now to introduce my co-host for this series, Bea Petner. Welcome, Bea. Every series session that we have, Bea steps away from her day job as a fashion designer with Kohl's, and we're always delighted to have her here. Bea, you now have the floor.
Thank you so much, Heidi, and welcome everyone. I'm going to start with the quick guidelines for today. So after reading these guidelines, I will ask our young participants to say their first name, the grade you're in, and additionally, if you have a piece of paper, scissors, and a laser pointer or any other light for today's chat and a demo happening in the chat, please leave your camera on if possible. Make sure you have good internet connection. If you can, change the Zoom name to your name if you're using someone else's account. Mute your sound when you're not speaking. Ask your questions as you think of them at any time in today's chat. Feel free to write your questions in the chat, and then Heidi and I will call on you to pose your questions to Judith. And then when asking a question, please repeat your name and grade. So with that, I'm going to kick off asking you to introduce yourself, and again, introduce yourself, the grade you're in, and if you have the materials for today. So Sophie, if you want to start.
Okay, sure. I'm Sophie Hack. I am in 8th grade, I believe. Yeah, I'm in 8th grade. Yeah, and I do have the materials, I think, paper, scissors, and I guess a small flashlight like this would be fine.
Perfect. Awesome. And then if Kevin, if you want to introduce yourself, user.
Hi, I'm Kevin Kanabe, but this is my daughter. Say who you are.
Olivia.
What grade are you in? Third grade. We will be collecting supplies.
Awesome. And then Serena, if you want to introduce yourself.
I'm Serena. I'm in 6th grade, and I think I have the materials.
Awesome. Thank you so much all. And now I am so happy to introduce our speaker today. So maybe in some of your STEM classes or STEM activities, you have been the only girl there. And if so, it might have felt intimidating or made you feel as though you didn't want to step in and lead. Well, our speaker today, Dr. Judith Olson, is a perfect example of how when you're the only female in the room, that is the exact moment to step up and lead. After earning her MS and PhD from CU Boulder, Judith went on to work for NIST, the National Institute of Standards and Technology. While at NIST, Judith was recruited to ColdQuanta to spearhead the organization's Atomic Clock Division. Under Judith's leadership, ColdQuanta will deliver atomic clocks that enable new capabilities in positioning and communications for use in industries such as aerospace and defense. As one of ColdQuanta's only female executives, Judith has laid the foundation and groundwork for other diverse candidates entering the organization. She was recently named the Next Generation Leader of the Year at the Women in IT Awards. Her accolades in leading in this traditionally male-dominated field don't stop there. Judith was also named the 52 Wonder Women working in the industry as Quantum Science and Engineers list. And today she will be talking about how the time for girls and women in STEM is now. And now, Judith, you have the floor.
Hi, everybody. I am Judith Olson, and I am hoping that today you guys all get to learn at least a little bit about clocks and lasers and some of the really important traits that it takes to be a good physicist. So I have a talk prepared for you guys today that I'm pulling up. The time for girls and women in STEM really is now. It's never been easier to embrace a science-based career and to get out there and really have the ability to succeed in doing science. And so I work as an atomic clock physicist. And I mean, how many of you guys here at least know what a clock is? Probably have one on your phone and everywhere in your house, and you use them for telling time. And usually you do this by, counting the seconds that a clock goes by. But another really useful way to tell time is instead thinking about the fact that, your minute hand goes around your clock once every 60 minutes, and your second hand goes around once every 60 seconds. So keeping time is very based on the frequency at which your clock ticks, how quickly it ticks. And atoms make some really, really good tickers. Atoms can keep very, very reliably ticking, and that's what we use to build these atomic clocks. Before I jump too heavily into that, I just do want to have a few minutes to talk about what it is to be a really good scientist. And this is kind of, at least for me, what would have been really impactful when I was about your ages, to hear this kind of thing, because I had this very narrow view of what a scientist looks like, what they're interested in, what hobbies they can have, but it really doesn't have to be that way. And I took a very kind of roundabout career to get here. I went to music school. I wasn't ready to stop playing instruments, and so I did a music degree and my physics degree. I love art classes and baking and hanging out with friends and makeup and getting my hair done. And there's no limit on what makes someone a scientist or not. And these are all hobbies and all sorts of things you can still pursue while also being a scientist. The two things you really need to be a scientist are curiosity. You have to want to ask questions, and perseverance, because often asking questions leads to more questions instead of answers. So it's about asking questions and then pushing on it harder and harder until you either get answers or have enough questions that you need to go do some more research first. So I hope everyone is well aware of the fact that, everyone can do science here, and it doesn't mean that is the only part of your personality. You still get to be a whole person and do all sorts of amazing things and be an artsy person or a musical person or just a very sciencey person. There's no limit on what makes someone a good scientist beyond asking questions and persevering with those questions. All right, so these questions are questions that really motivated me in my early days of being a scientist. And I distinctly remember in second grade, my first real big experiment, and that was to figure out what silly putty was. You guys have probably played with this. It's stretchy, goopy stuff, and it kind of melts, but it doesn't melt. And I just was so confused by silly putty. I could not understand how it worked. And so I started taking data on silly putty. I would measure, how long it would stretch and how much time and what different shapes you could make it into and how long it would hold that shape and all sorts of things. And at the time, I just thought I was, having fun with silly putty. But in retrospect, that was like one of my very first big science moments. And it kept going from there. By third grade, I became really obsessed with color and light and how light works, how it magically travels through the air. And why are things different colors? What makes something red versus blue or orange? Why is everything like that? And so all of these questions helped spur more questions. And I will be answering some of these at least today. But for now, I want to make sure that you guys have an idea of what kinds of questions you might start off with and how those questions grow as you learn more. So by middle school, I knew I had a general idea of how colors worked and why things were different colors. And I became really fixated on light. How does light work? How can you have a light bulb somewhere and the photons, the light shows up somewhere else. How does this work? How can light go through glass? It's a solid. You can't put water through glass. Why can light go through glass? So I started having all these questions, and that resulted in me asking some very sciencey questions by high school. I really wanted to know what photons were and how they worked and what quantum mechanics was. And I think it's just important that this was all very gradual. It seems really scary to be wanting to learn about these big concepts in science, but when you're learning slowly over time, it's no longer scary. You get in there and one day you wake up and quantum mechanics isn't that frightening. It just takes perseverance and asking lots of questions and continuing to move on even when you don't get the right answer always. So this is one of the first experiments I did when I was much younger. And for this, all you need is a flashlight. And it's probably something you have done a few times before, but maybe not necessarily realized quite what was going on when you did this. So if you have a flashlight and you put it up behind your hand, you can see the light go through your hand. And if you have bright enough flashlight, like in the picture here on the slide, you can see all the veins and the bones in your hand even. And that to me was really cool, because that means that there are photons from the flashlight that are traveling through your hand and reaching your own eyeball in order to see it. And for me, that was really crazy because nothing else can go through your hands. Like you can hold water in your hands. Air doesn't flow through your hands. Your hands are solid. And so the idea that photons and light kind of played by different rules was very exciting to me. And I wanted to learn more because if photons can go through my hand, they can do all sorts of cool stuff. What else can they do? And that really inspired me to keep pushing down this route that led to where I am today. In order to study light in a scientific laboratory like I do, we like to use special kinds of light that make some of our studies easier. In this case, we use lasers. Got 3 laser pointers here. Lasers come in all sorts of different colors. There are red lasers, and there are blue lasers and green lasers. And the thing that really makes lasers special is that they are just one color. There's only one wavelength of light really in a laser, as opposed to something like a flashlight, which has a very white light. It's composed of many different colors. And that's the thing that really lets lasers be special, because it means all of the photons, all those little particles of light, are going to behave the same way when they go through an experiment. And in this experiment, we're going to be putting them through a tiny slit of paper. So this is some pictures on the right here of the laser labs I have worked in. And lasers, because they are just of this one exact wavelength of light, can be very useful. And they're also very directional. You can shoot a laser pointer across the room and it stays very, very tiny, even from a distance. Whereas a flashlight, as you move further away, that beam size gets much bigger and harder to see. So those are just some of the reasons why lasers are really cool tools to use while playing with light. And in the case of lasers, you can start doing some really interesting things by sending them through small holes or slits that are very, very tiny, so tiny that they're kind of near the wavelength of the light, thinner than a piece of your hair. So that's the first set of experiments we're going to do today, involving diffraction. And I like to think of diffraction as, I don't know if you've ever seen like Avatar: The Last Airbender. It's like light bending. You're taking this laser pointer that normally goes absolutely straight, and we're going to be able to make actually some of the light turn a little bit and go at a slightly different angle. So for this demo, you need a piece of paper, some scissors, and a laser pointer if you have one. And if you don't, you'll still be able to have fun with a flashlight, I'm thinking. So first step is you need to make this little tiny slit in a piece of paper. It needs to be very, very small, so small that it's hard for you to even, it takes me a few tries usually to cut a small enough slit. So usually what I do to help do this is I take my piece of paper and I fold it in one section. Fold it flat. And you take your scissors and along the very edge of the paper where you made the fold, barely take away any paper, just the tiniest little slit you can imagine. Just laying about the width of a hair. And when you're done, you should have a very, very tiny slit in your piece of paper. I've got a few in mind from earlier. And if you make your slit too big and you have a good laser type source and you're not seeing the effect, it usually means you just need to make an even smaller slit in your piece of paper. So does everyone have some paper ready? So I'm going to show you what happens when I do this experiment here with my laser pointers. So I have my handy dandy pizza box that I have put some paper on here to act as a board for you guys. I'm going to take my piece of paper with our little tiny slits in it. And if I shine my laser light through the tiniest little slit over here, you can start to see some interesting effects, especially as you move the piece of paper further away from the wall. So I'm not sure if you guys can quite see it from here, but there, the shape of the light as it hits the paper is no longer just a dot like you'd expect. Here's the laser pointer without anything. And here's the laser pointer going through the slit. And if you look really closely at this image, it kind of looks like what I have up here on my screen, the red and black image at the top with lots of different dots. So you should be able to do this with a slit of paper. Again, for the lasing source, my laser pointer's not happy. For the lasing source, you can usually get to see some of the structure that goes behind the laser itself and see those little dots. But if I use a regular flashlight, you don't really see anything. In this case, you can actually learn a little bit more about the flashlight itself and how the diodes inside of it are lined up. And that's what that big central dot is. But other than that, you really just see the one slit. Now, in case this demo was not working well at home for any of you guys, or it was hard to see on my computer, I did set up a special system that lets us get even better diffraction. And this is something you definitely want to make sure you're doing with a parent or somebody around who's careful. But razor blades work wonderfully for making precision slits. We use them a lot in labs too, because they have such a perfectly straight edge. So I have taped two razor blades together and I can move them together and apart to form a slit, just like you guys were doing with the piece of paper. I'm going to do that now while you see on the board. It's a lot easier to see the diffraction pattern this way. So, back to the board. Getting my laser lined up. I hope you guys can see that. Holler if you can't really. But there's this line that forms where the laser is that gets bigger and smaller as I move the razor blades further and closer apart. And lots of little tiny dots on either side of that central dot. So hopefully you guys were able to see that and maybe even see it at home. If you're struggling to see anything like this at home, it can help to either make a smaller slit in your paper or to make sure that the surface you're looking at the image on is much further away. And if you guys are having trouble getting this demo to work at home later and have any questions, feel free to bring me up and let me know so I can try to help. The diffraction. This is a really cool thing that lasers can do, and it lets you bend light in interesting ways. And this happens here because light is both a wave and a particle. It's a lot like, you know, if you're at the pool with your friends and everyone's bouncing around, and if you guys happen to go up and down at the same time and bounce, you get a mega wave that's like twice the height. It's a very similar thing here. When your light is going through this slit, it can actually travel through, you know, many different portions of that slit. And at some places, the light all lines up perfectly from your laser and you get a big bright spot. And at other places, there's a big wave up and there's a big wave down and you wind up not really seeing any light, and that gives you those dark portions there. So I always thought that was really cool. And it's a way to kind of start seeing the edges of the quantum world in our everyday lives. So why does this work with a flashlight then? If you have a regular flashlight and you do the same thing, you really just kind of see your main slit. Maybe you see some sort of a circle from the flashlight bulb itself. And the reason this doesn't work is because white light has all these different colors in it. And the amount that these colors bend when going through the slit is dependent on the color itself, on the wavelength of the light. So the image we have over here showing diffraction shows, for instance, that the red part of the light goes a lot further out at an angle than the blue part does. And that means that they're all kind of creating these bright spots at different places along your wall or whatever surface you're using to look at. And this means that all of those little dots that you see with a laser wash out and you can't really see it anymore. So now to dive in a little bit more and try to if you guys can hang in there for some more physics about how lasers talk to atoms. Atoms in this case are these small little fundamental building blocks of nature. They're kind of one of the smallest divisions we can have. If you zoomed in with a microscope 1 billion times over, you might start to see atoms. And when atoms interact with a photon, it can cause the electrons, these floating orange dots outside of the center of the atom, it can cause those to move around and go from what we call a ground state, when you're kind of just bored and sitting there, to an excited state. They get all energized up and they want to move around and maybe even have the atom shoot one back out. So I've got my atom here. I send in a photon. The photon gets the electron all excited. The atom eventually gets tired. It shoots the photon back out and it goes back to its ground state. Often in science classes, rather than drawing the whole atom like this, you usually just see kind of the 2 levels that the electron went through, because it's a little bit of a simpler picture here. So you have some ground state where the atom is all rested and collected. Then you have this excited state that it gets into if it has a photon of the right color come by. And if you have your laser pointer and you're doing this kind of experiment and you can change the color of your laser a little bit, it doesn't have to be a lot. You can start to see how the atom responds as you get close to being at the right color. When you're at the right color, the atom responds a lot. And when you're close to the right color, it responds a little. And if you're nowhere near it, it doesn't respond at all. And we call these, as you change the color of your laser, spectral lines. And the center of the spectral line is often called the resonance. And so there are a lot of resonant phenomena that you might have seen. This happens with, musical instruments, all sorts of things. If you've ever been in the car and the radio is playing a loud song and a piece of plastic starts buzzing, or you're playing an instrument or the radio loudly and you hear a cup rattling in your cupboard suddenly, that's resonance phenomena. It's having energy interact with something that is at just the right frequency or just the right color in the case of a laser to make something happen with this object. So if we do have light interacting with our atom and it happens to be at the right frequency or very close to it at the right color, then the atom will start reacting. This means that the atom is giving us a sign when our laser is close to the right color or right frequency. And this kind of forms what we eventually use for atomic clocks. So when you have light interact with your atoms and it's at the right color, it's at the right frequency, your atoms will start sending light back to you as well. And it's a really clear signal that your laser is at the right color. And this is how atomic clocks work. We're trying to take this frequency of light that you're using in your laser, we shine it at our atoms, and if it's correct, the atoms fluoresce a bunch, they send out lots of photons. And if it's not, they don't send out photons, or maybe they only send out a few photons. But that means that the atoms, they're doing all the hard work. The atoms are telling us when our laser is at the right color. And that is how we're able to stabilize the color of our lasers. And this color, this frequency, can be used for timekeeping. The same way that in a clock, your second hand goes around every 60 seconds. Lasers oscillate much faster. They have, hundreds of terahertz of oscillations in a second instead of, a 60th of an oscillation. But that's how we end up making atomic clocks. So just to try to help animate this, to maybe make things make a little bit more sense. We've got our laser diode down here below the graph. We've got our atoms in this pile over on the right. We've got some sort of a detector that will tell us if the atoms are shooting out photons. And then we can use some electronics in the lab to take the size of the atomic response, how many photons these atoms are shooting out, and use that to correct our laser frequency. So if the atoms are only shooting out a few photons, we know our laser frequency is close, but not right, and we need to nudge it. If it's not shooting out any photons, we know that the laser frequency is totally wrong. And if it's shooting out a lot of photons, we know that our laser color, the frequency, is right at the right spot. So if you take your laser and you start changing its frequency, the atoms won't do anything when you're far away from resonance, but as soon as you hit near that peak, as soon as your laser is the right color, suddenly your atoms go crazy and you see lots and lots of photons. So this process is exactly how we make atomic clocks. Some of these clocks are a little bit more complicated, but it's the same idea that we take light, we interact it with atoms, we change the color of the light a little bit, and the atoms tell us if we got closer or further away from the color the atom wanted. This only works really well though if the atomic resonance stays fixed. And so atoms, luckily every atom is kind of identical, and that's really convenient. But there are things that can cause this resonance to move around. And that's really the hard part of my job, is figuring out how to keep the color that the atom wants to see consistent. How do you keep that the same so that your clock is always ticking at the same rate? And then just here at the end, before we go into some questions, I also just wanted to kind of show you what a day in the life of a physicist might look like in grad school and things of this nature. This is one of my first big experiment build-ups in grad school for physics. And I needed to build a blue laser that had photons at 431 nanometers. They don't sell lasers, at least they didn't at the time, that are that color. So I had to make one. And they have this really cool process where certain crystals, if you put light through them, it will double the frequency of your light and it will change the color. So I put invisible light into this little tiny crystal, and out comes bright blue light. A lot of it too, which is very convenient for what we're doing. So the process of making this work was going through and figuring out exactly where every piece needed to be, planning out how all of this would work. But the fun part is getting to be an experimental physicist, at least for me, and getting to actually build this thing and then see it in the lab. So this beautiful blue light you see in the picture here is actually a picture of the laser system I built for our lab in Eves, which I thought was a pretty cool project. So I have some questions for you guys, and I'm sure you probably have some questions for me. And I'd like to have a chat if you guys are up for it.
Yes, and then also just as a quick, thank you so much for that amazing talk. If you do have any questions, feel free to place them in the chat and we will call on you to unmute yourself, say your name and your grade again. And then just a reminder, every question is a good question. So please jump in, ask any questions, and yeah.
Anybody want to go first? Well, if there aren't any questions, I could try showing you the laser demo again, or I could talk a little bit more about my path to becoming a scientist. It really depends on what you guys are interested in.
I was just about to ask how you got onto that path of atomic clocks, but yeah, I'd like to hear about that.
Yeah, so I knew I wanted to study atoms and light. I thought that was really cool. I had a lot of questions about how that worked and why that worked. And as I learned more and more about physics and atoms and how everything comes together, I really liked learning the deepest depth detail I could possibly dive in this. What is it that makes atoms so good at interacting with lasers? And how can you use those interactions to do novel, special things? So for me, atomic clocks were kind of like the most pure form of this. It's almost like if you were studying violin or something like that, and you only ever wanted to play Vivaldi. Like I had this niche that I really liked in physics. And atomic clocks are the study of those resonances in atoms. They're the study of how light and atoms interact, and specifically how you can use the atom's reaction to do other interesting things with your lasers. And also a lot of science too is kind of just the path you wind up in. Like I knew I wanted to study these things, but where I went to undergrad didn't necessarily have one of those programs. They didn't have a lab studying atoms and light yet. So I actually went to one of my professors, was like, I really want to study this. I want to make an experiment. Let's get funding. And we wound up setting up the first lab studying atoms and lasers at Ithaca College, where I went to undergrad. There's a lot of ways to get in there and to find support to help you study the things you want, even if it's not atoms and lasers. Are there any other questions or information you guys might like?
Olivia had a question about, she saw your lab set up.
Yeah.
And there were just so many pieces in it.
So many.
Question again, was it how she came up with them?
Yeah, and how does all your labs have all that amount of pieces? Yeah,
it looks very scary and complicated when it's all put together, even to people who have PhDs and have been doing this for a long time. It's a lot of things to have to consider and think about and plan for. But it's not that scary if you break it down into small pieces. And that's the same approach I use for solving all my physics problems, is to find sort of a yes or no question that you can start off with. You know, what color do we want our laser to be? So we go off, we buy a laser, we get to look at the laser and say, is this the right color? And that's a good starting point. And from there you go, all right, the laser is coming out of my laser source. It's right here. But where do I want it to be going? You know, which mirrors might you need to get it to the location you want? And you can start asking more and more questions about what properties of the light you need to care about. Things like polarization and lots of big scary terms that take a while to understand. But just like all things in science, it's about taking small steps. And before you know it, you don't realize that you've gone a really, really long way from where you started.
Sophie has another question about atoms. Sophie, go ahead and pitch your question.
Yeah, basically, my question is, do atomic clocks ever make mistakes?
Yes, all the time. Rarely, though, is it because of the atoms themselves. The atoms are kind of perfect. The atom will do exactly what we expect it to. The harder part is putting the atom in a situation where it gets to do what we want it to. So in order to get these atomic clocks, you have to go through a lot of effort to make sure that the atoms are very isolated. Usually we put them in vacuum environments, so they're not even interacting with particles in the air around us. And this helps insulate them from other interactions that we don't want them to have. We really want to make it so it's just atoms and our photons that are interacting. But there are so many different things that can show up. A lot of the errors in clocks actually aren't due to the atoms, but they're due to the software. They're due to how we interpret what the atoms are telling us. And it's really easy to misinterpret what an atom's telling you since it doesn't speak English very well. It just it emits photons or it doesn't. And you have to really study a while to figure out how to tell what the atom is actually trying to say to you, if that makes any sense.
Judith, what colors do the atoms respond to?
All sorts of colors.
Okay.
I'm a little bit biased. I like visible light and colors that I can see that are all sorts of pretty colors. So in this picture here, this was my graduate work experiment where we had blue light at 431 nanometers. And we had this red light at 657 nanometers. If you have a red laser pointer at home, it is likely a 600, I lost my red one somewhere. It's likely 650 nanometers. So there are all these colors of light, any color that you can see with your eyes, we can make a laser that color. And there's probably an atom out there that would respond to that color of light. But there are also colors of light we can't see with our eyes. There are infrared, there's ultraviolet, all sorts of colors that like only bumblebees or certain fish normally see with their eyes. And atoms still respond to that. Atoms even respond to thermal energy. Just having, the temperature of your skin, you're actually emitting light. It's very, very dim compared to room lights and things. You can't really see it, but the atoms are so sensitive that they can see it. And it's really important then when you're doing these experiments that the atoms are only seeing the photons you want them to see. Otherwise, these other particles of light that interact with your atom can make it so your clock doesn't tick at the rate you really want it to. Does that make sense?
It does make sense, yeah. And I'm wondering, I want to make sure we get all other questions in that the girls may have. And I'm wondering if you have some insight you can share about when you get a question, what do you do with it? Like, how do you keep your curiosity peaked and flowing?
So the thing that works best for me in this case is usually to ask a question so that I know what I don't know or what goal am I trying to get. The question helps orient me. And then that usually leads to more questions. And it becomes an effort of deciding which questions are most interesting or might give the best information. And it really is just about finding things that are interesting to you. There's no one path to study science. There's no one specific laser wavelength that will teach you everything you ever need to know. It's always about trying to collect enough information to make a decision. But often that information, it's too much for any one person to know. So you really just have to decide, what do I find interesting? What questions do I like asking? And then study things in a way that lets you ask more questions. And if it's not as interesting to you, there's always 10 other ways you can go. instead. You could ask 10 other questions that might not be about, the color of your lasers, but maybe what power source do you need to make lasers work? Or what makes a laser work better or less well? There are all sorts of questions you can ask, and it's just about, where your brain goes. What do you find interesting in that moment?
Got it.
There's really no wrong answers when doing physics or science of this level. It's just about asking more questions and figuring out what you find interesting.
So there's no failure, which is
Oh,
beautiful.
there's lots of failure. But a lot of times those failures are great learning experiences. You don't get through grad school without breaking a lot of equipment and saying a lot of wrong answers at some point. And the important part is that rather than saying, oh no, I did this wrong or I broke this thing, is that you say, all right, what did I learn? What could I have done differently? What questions could I have asked instead? What do I wish I knew before I got there? To better understand how you can learn and move forward. Because you're gonna mess up. Everybody messes up. It's not just a science thing. It doesn't matter what field you're studying in, you're going to make mistakes. It's about learning from them and moving on.
So how many times did you mess up on this laser, Judith, before you actually got it working the way you wanted?
Oh, so many times, hundreds probably. It's really easy to make mistakes when you're trying to talk to atoms because they're so sensitive. If you accidentally put your thumb on one of those mirrors, it can cause the light to not bounce off of it, right? And cause all sorts of problems. So there's a lot of mistakes you can make that don't even feel like mistakes at the time until you go back. And those are the fixable mistakes. I also definitely broke my fair share of equipment. I've started a few lab fires. There's lots of beautiful mistakes you get to make along the way while learning. Always keep a fire extinguisher nearby if you're doing anything flammable.
I have one more follow-up, Judith, for you. At what point did you have to stop having fun to become a scientist?
Never. You never stop having fun. If you have curiosity and you're interested in things, it always winds up being fun again. There's a lot of hard work. There are some frustrating days, but the fun I have getting to do this outweighs all of that. And I hope that it helps inspire the passion and the fun for doing science in you guys.
Would everybody use the chat to write in the chat now what your favorite part of today has been? Like your favorite takeaway, your favorite thing that Judith has shared. Everybody, if you'd take a moment just to put that favorite thing in the chat right now. And this has been an exciting discussion. And Judith, we want to keep going.
Okay.
If girls have questions for you following our sign off for this evening, how can they get a hold of you?
I have an email address that you could send out. That would probably be the easiest way.
All right.
I feel like ColdQuanta would also not mind giving tours to anybody who might be interested in seeing some of our laser systems if they live near Boulder.
Okay.
And again, if you guys have any questions, I love learning more about science. I love learning about what other people like learning about science. And so if you have any questions or just even, want help figuring out what good questions might be, feel free to reach out. I'd love to help.
Okay. Okay. So are we getting the logs in there in the chat? Okay, great. We've got some going in. Everybody put in your favorite thing.
And as those favorite things are rolling in, and it's so great to start seeing the initial ones, just a huge thank you so much to you, Judith, for your amazing talk, for the great questions and discussions. Also, a huge thank you to everyone who has made She Has a Floor a success. We started shortly after the fall equinox, and today we are ending on the winter solstice. So a huge thank you for the whole series. Thank you so much to Pretty Brainy's partners for this series, JILA and JEDI at the University of Colorado Boulder. Thank you to ColdQuanta for joining us today. And then also thank you so much to girls and families for being here throughout all of the weeks and all of the series and for today. Please keep staying curious, keep asking questions, and thank you all so much. And Heidi?
Thank you to our fabulous team. Thank you, Bea, for co-hosting. Thank you to Crystal for her amazing she's the glue that puts everything together and keeps it moving together and forward. And we couldn't do without Crystal Bordner. Thank you to our board members, Mina Bogopal, Dawn Putney, Robin Steele, and to our amazing community for all their support. And everyone, happy holidays, and we'll see you in 2022. Thank you.